going, but don't start yet because I'm going to do introductions for the first time in a long time. All right. Hey, everybody. Welcome once again to another exciting episode of Zig Ball Z. Today we have with us Niles. Thanks for joining in. I'm just going to go around the room and does anyone not want to be seen on the internet? Okay, no objections. All right, cool.
Andrew.
Then we got Andrew.
Dan.
And Dan.
Brian.
And Brian.
And Jeff.
And Jeff.
Robert.
And Robert. And yours truly, the agitator, AJ. So I want to give a quick shout out to thank Jeff and Vivint for giving us a nice place to meet and eat and drink and be merry, especially during this fanciful time of year. And let's see, is there anything else that I should say before we get started? Like, sub, follow if you want to. It's pretty much the Niles channel most of this year, but it's that's the way it needs to be.
Yeah, I guess so.
All right, so with that out of the way, thanks everybody for coming. Remember, this is a safe space. We burp, fart, and break things and say inappropriate things at inappropriate times. So you're welcome to be yourself. And with that, we'll go ahead and have Niles present on an intro to SIMD as it relates to Zig.
There you go. Yeah, as you said, my name is Niles Salter. You can find me at Validark on GitHub, or yeah, that's pretty much it. So I have this one is going to be a little bit more low key than my other ones. I didn't make a ton of slides for this one, but I do have an itinerary here. I'm going to cover what is SIMD and why, how one can wield it. So first I'm going to open up Godbolt so people can see how we set that up. And then I'm going to show like how much can we expect the compiler to do for us. This is the first question that most people have once we start getting into it. And also, what can we even do with SIMD? I'm also going to go over how we can find the intrinsics, and might mention some other resources. Okay. So, what is this? Yeah, let's do the definitions first. SIMD is single instruction multiple data. I also included SWAR right here. That is SIMD within a register. So what exactly are we talking about? The idea is we have a series of instructions. On the left, you can see some x86 assembly. We just have 4 add instructions. And this can actually be represented with a single instruction, which is going to do 4 adds. So that says VP add Q. V is your it means vector. P actually means pat, I believe. And then Q in x86 lingo, it refers to a quad. So a quad word is what it is. A word a long time ago was 16 bits, and the terminology has persisted. So a quad 16-bit is going to be 64 bits. So this is saying we're doing 64-bit adds, and then you can see that we have these YMM registers here. So a little bit anatomy of an instruction. If someone's completely unfamiliar, we have these registers here, and these are going to be named locations like a variable in a program that the computer can actually interact with directly. So it can take data out of that's associated with RDI and data that's associated with R8, add those together, ditto for the rest of those. And these are what are called scalar registers. So that just means it can hold 64 bits on a 64-bit machine. The fact that they start with R tells you that for x86. That just happens to be, if you look up how the x86 registers have expanded and changed over time, they just made R be the prefix for 64-bit registers. And on the right, you see completely different registers. So this is a YMM0, YMM1. What these are actually 32-byte registers. So each one of these can hold 32 bytes. It's like a 32-byte variable on the CPU. And yeah, this VP add Q has 64-bit or 8-byte granularity. So that means you're going to be doing 4 adds at once. And Yeah. So why is this helpful? Number one, it decreases the instruction count, and that reduces pressure on the CPU front end, which is good for the decoder, scheduler, and I-cache, instruction cache. And I have a point here. That lowers the power usage, which can result in higher clock speeds. Because yeah, the front end of a CPU is no joke. We've argued here before about RISC versus CISC. Is it better to have fewer instructions that do more, or more instructions that do less? On a modern high-performance machine, typically you actually want fewer instructions that do more from the perspective of the CPU front end, at least, because your decoder and scheduler and other caches in the front end, they are doing a tremendous amount of work. We have these out-of-order superscalar machines, so that means that they can change the order of instructions and that they can do more than one instruction per cycle. They can start more than one per cycle. And so, actually this laptop that I have here, it can actually do those 4 adds in a single cycle. And it can conceivably do a VP add in a single cycle as well. This one will actually do it in 2 cycles due to a Zen 5 regression, actually. But the reason why this is helpful is, actually having fewer instructions go through the decoder and then go through the scheduler. So the scheduler is working out what are the data dependencies. So it's going to have to look at RDI, R8, RSA, R9, all of those, and figure out when are they produced, when are they going to be ready, so that it can actually do this add. And we cut that down by a factor of 4 here. So we can do 4 adds in a cycle with 4 add instructions, or we could do it with a single VP add queue. That also means that we can actually duplicate how many add queues we want to do. So we can have 4 of those. This machine can actually do 4 of the scalar adds or 4 of the vector adds. And so we can do significantly more on larger registers if we have enough work to do. It also makes pipelining more likely. So pipelining is a concept that my favorite example of it comes from a video Casey Muratori did, where he explained that it's actually a lot like having a washer and dryer versus a washer and dryer combination. So he's like, okay, if it takes 1 hour to wash your clothes, 1 hour in the dryer, or if you buy one of those machines where it will wash and dry in 2 hours, which one is going to be faster? And for a single load, they're going to be the same. But if you have multiple loads, once you finish the first wash, you can put a new load in. So that's the basic idea of pipelining, which is that you can have each individual unit be active at once, and so things can be moving through the pipeline. And that means that each additional load of laundry in the example would take 1 additional hour rather than 2. And so you see this with code as well, where we might have a loop which maybe does some complicated things, and it may only take 1 additional cycle per extra iteration that we have to do, even if each iteration itself, even if that takes 100 cycles. With pipelining, we only pay the cost of the latency a single time, basically. Okay, we can increase the amount of work per instruction. Yeah, we can only execute so many UOPs per cycle. So I sort of mentioned that we can do 4 adds in a cycle. We can do 4 VP adds in a cycle as well. So we can do significantly more work with SIMD. We can actually mix and match. We can actually do scalar and SIMD at the same time on the same cycle. And yeah, so now I want to show a little bit of Godbolt. Let's open that up. For those who missed it online, I'm using an experimental pre-alpha Cosmic DE from Pop!OS. So I don't have screen mirroring, so I just have to look at the screen. Okay, so this is Godbolt on the web. And you can see this is how much code it takes to multiply in debug mode. So the first thing we want to do is turn on optimizations. I'm actually going to go to release small first. So we can do release small. Let's turn up the text size a little bit. And then let's target a CPU. So let's do CPU. Let's say mine, Zenver 5. And then let's just make sure the target is set. Target. Missing an R. Target is set to Linux. Like that. And that doesn't work because I messed something up. I might have done it backwards. Let's undo that.
Do you need an equal after
I don't think you do. Oh, does it say that it doesn't? Oh, it's because the version of Zig doesn't support this computer yet. This is a brand new architecture, and so only the newer Element actually supports Zenver 5. Okay, there we go. So, so the first thing I want to show is what it looks like when we try to let the compiler do its thing. So let's just take that that basic example again, and let's do accumulate with A. And yeah, let's take in some numbers, and that's going to be a many item pointer to some U64s. And let's take in a length, which is going to be a pointer pointer-sized number. And then let's return a U64. Okay. So let's say var sum equals 0. And let's give it the type of U64. And then we do for. By the way, the reason why I'm not using a slice is just because the C ABI does not include slices, because C did not include that type. And so, so in order to export it, I'm just not using the slice type. The slice type looks like this. You just take that out, and then we wouldn't need length. That would be a part of nums. But the C ABI doesn't use that because C does not have that.
Wait, and we need the C ABI because why?
Because I'm exporting the function so you can see the output in Godbolt.
Okay.
What we could do is we could like export a separate one because yeah, this is like a C compatible export. So I could export accumulate external. And I can take this and then we can pass it in as a slice this way. Like that.
C is a fun language. You don't need slices. You don't need errors.
So yeah, let's just iterate over the nums and add them together. Just gonna do that. Okay. So this is on release small, first of all. So that, I just want to show this first before you get scared. So you can see we do we XOR a variable with itself right here and right here. Anything XORed with itself is 0. So this is a very common idiom on x86 to just 0 this register. This can actually be done in 0 cycles to the back end. Yeah, fun fact. And then we can do a comparison between RSI and RCX.
So
that would,
could you explain these letters for
Sure.
me? I don't know if anybody else has a problem with it.
Sure.
I don't understand this.
Okay, so which part should I start with?
So why is it called RSI? Why is it called RCX? Why is it called
Sure.
ECX, EAX?
Yeah, let's start with that. Let me type in x86 registers. Oh,
Is Z86.
ZX6.
It's even newer.
There you go. Let's try this one. So these are the register names of the general purpose registers right here. So originally they were called AL, BL, CL, and DL, and yeah, these were the original names right here. Actually, even before the x86, and they kind of corresponded to accumulator, base, counter, data, source, right? So this is like a variable name that people would commonly use because people would write in assembly directly. And so like the newer registers are actually, do we have it on this page? No? Do I have Control F? Okay. It's not there. But the newer registers are just numbered. And so you just have like R9, R10, R11, R12. But just for historical reasons, they're named accumulator, base, counter, data. That's all it means. And
Okay, so if I see A in somewhere in there, it's accumulator, B somewhere in there, and the X is for the number 1, 2, 3, 4, 5, 6, 7, 8, 9.
yeah, so you don't actually have to know this. This is like, this would be a convention. So if someone actually was, this is actually a good example, if someone was writing an accumulate function, by convention, you'd stick it in the RAX. You know, RAX would be your sum. And in this case, that is what it's going to be. Not because the compiler figured this out, but actually because the return value goes in RAX based off of the ABI. That's the application binary interface. So when we export this as a C function, that accumulate external, which you see the label for in line 1 on the right, it has to return it in RAX. And then the registers that it takes in, this is specific to Linux. So if I actually change this to Windows, it's going to be a little bit different what the convention is. But yeah. And yeah, so you get, I think, RDI and RSI, which are also aliased by EDI and ESI. I might have gotten that wrong though, right? Or no, I got it right. RDI, and then looks like we're looking at, yeah, so what we do is we zeroed RCX right here, and then that's going to be the same as RCX. So how this actually works is this was expanded over time. So we started with 8-bit machines. x86 actually started as 16-bit. And then we eventually got 32-bit registers and eventually got 64-bit registers. And these are extensions of each other. So if I XOR EAX with itself, that's actually going to XOR the full 64 bits as well. And the reason why they write it like that, or why they do that, I think it's actually 1 byte shorter in the instruction, like the bytes that get passed to the CPU. You don't have to actually like represent it like that in the assembly, but they do, just to be nice for people who want to know that detail or something. But yeah. So yeah, what we're talking about here is you have these 64-bit registers, and they have different names. And so ECX is one that we zero. EAX is going to be our return value, which is the same as RAX. The key one here is the A and the X.
Okay.
So ignore the first letter in some sense.
So that's just an annotation of how it's used?
Yeah, what that tells us is how much of the register it means to use as part of the instruction. For the good instructions, it will zero the upper 32 bits when you're doing a 32-bit operation.
But they're just registers, and
They're-
the
yeah,
different
they're just
names are
names.
just historical reasons, essentially.
Yeah, so it's like a name in your program. So RAX is your sum, because that's your accumulator. And ECX/RCX, that's going to be a counter. So you see we're doing a comparison between RSI and RCX. So RSI is probably our length, right? And we say, okay, we did a comparison. If they're equal, we're going to go to this label here, which is this one, which means we return, we're done.
Okay.
If they're not equal, then we keep going. We add RAX, that's our sum, to this thing here. So what this says, this is actually a pointer dereference in assembly. Anytime you see this pointer annotation and then this brackets, this is a pointer dereference.
This is actual assembly, huh?
Yeah.
Huh.
So, this is a representation, right? It does have a binary form as well. If you click this, it will actually show you. So these are the bytes that will actually get passed to the CPU to actually do this work in hex.
Okay.
So let me turn that back off. But yeah, this is the Intel assembly. There's actually a few conventions for x86, the other major one being AT&T syntax. But yeah, this is Intel. I strongly prefer it. Yeah. So yeah, we're going to dereference RDI. We're going to add 8 times RCX. So the reason why we're multiplying here is because RCX is going to RCX is being incremented each time, and we're comparing it against RSI. So what this is actually doing is we're comparing against the length, and we're saying, okay, if we didn't reach the final element, we're going to add. We're always multiplying by 8 because there's 8 bytes in a U64. That's why.
RDI is the starting point.
RDI is the starting pointer.
So it's the offset of the starting point of the array where the next number is.
Right. Yeah, so RDI is this nums here, and then RSI is this length. And yeah, so we say, okay, start of the array plus RCX, which is our index, multiplied by 8, because we're talking about 8-byte elements of the array. And then that will add it to RAX, right here. And then we increment RCX, and then we jump back up to 1. And we just keep doing that. So we say, okay, did we reach the end? Like, is the length equal to the index? If it's not, add it again, increment, jump back up, keep doing it until they're equal, and then we return.
Okay.
So hopefully you can see how this is the same as what I wrote up here.
The names of the registers is confusing because I'm not familiar with them.
Yeah.
But I get what you're doing, and I did this at one point in college, so it's there somewhere.
All right, so this was release small. This was the easy version. I want to show you what release fast looks like.
For real, man.
Yeah. So this is 50 lines of code here.
That doesn't look like it would be faster.
Well,
It's the looping.
well, yeah, let's see why. So first, we're pushing the base pointer. This is some stack management stuff. Then we move RSP into RBP. We test RSI. And then,
Sorry, again, for
Yeah.
my benefit, I don't want to hold other people up if everybody else gets this, but would you, as you're explaining the registers, just summarize what that was again? B was,
it doesn't matter. It's just a name.
And
well, it
the-
represents something. Like, I don't understand
Oh,
what it
yeah.
represents.
Those first 2 instructions, though, aren't part of the main logic.
Yeah,
those are stack
This is
management.
the stack pointer. This is some stack management stuff. So
That has to be there for every function. Depending on what convention you're using, it either goes inside the function itself or it goes inside the function that calls your function. That just always is there.
yeah,
It's not
anytime
important.
you want to use the stack for anything, you have to do a little stack management. The compiler just inserts this for you, so you don't have to worry. So we test RSI against RSI. So this is going to be our length. And then you see we do a jump on equal. This is actually going to be equivalent to, yeah, let me just explain what this means. This test instruction, we are doing an AND, actually. So it's going to be RSI ANDed with RSI. And then what we're actually reading in this next line here is whether or not it's 0. Because the test instruction will set some flags and a flag register. And the point is that this jump on condition, jump on equal, can read the flags. And so we're actually testing, is this equal to 0? If it is, go to this label that's highlighted. And then we just XOR EAX, we pop from the stack. So that means we just zeroed the result. So what we're saying is, if I pass in a nums array that has a length of 0, the sum is 0.
Yeah, got it. That makes
Okay.
sense.
Okay. Next, we compare it RSI to 32, and we say if it is above or equal, go to number 4. Otherwise, we zero these out again and we go to 7. I actually want to look at 7 first real quick. Okay. Yeah, let's go back up here. So we say if RSI is greater than or equal to 32, we jump in here. And this is getting us set up for the loop that is right here. So the first thing we do, like we're just moving some constant into RCX, which is negative 32 in this case. And then we XOR all of these registers with themselves, so they're all 0. And then we XOR EAX as well. That's our accumulator, probably. And then yeah, you can see we do this VP add Q, like I was showing before. And again, we take the base of the array, the nums pointer, and then we take RAX. So I guess RAX is actually the index for now. But at the end, it has to be the return value. But yeah, so we take 8 times RAX, we add it to the start of the array, and that is a ZMM word pointer. So how this actually works for the SIMD registers, we have XMM, YMM, and ZMM on x86. And XMM is 16 bytes, YMM is 32, and ZMM is 64. This is only supported on the AVX 512 machines, and I have one of those. So this is saying we read in 64-byte pointer. That's what this means. 64-byte pointer, this is the address that we calculate. We dereference it. It gets read into an immediate ZMM register that we don't need to name, and it gets added to ZMM 0. And we do the same thing for 1, 2, and 3. Then we add 32 to RAX, which is, again is our index. And then we compare it, and then yeah, if we're done, if we reach the end, then we do some cleanup stuff. So this cleanup stuff is going to be called an epilogue. And you can see what we're actually doing here. We add 0 and 1, we add 2 and 3, we add the result of those two together, right here. And then these instructions here are actually meant to reduce it horizontally, is what they call it. So what we're saying is we have 4 vectors. We're reading in 32 U64s each time. We do a comparison. And yeah, we keep doing this until we run out of 32 of these numbers to add at once.
So once we fall down to, say, 5.
Once we fall down to, say, 5, yeah.
Okay.
And once we fall down to 5, then we add those 4 vectors together. And then within the single vector, we find the sum of the values that are in that vector. So we do, what do they call it, a horizontal reduction. And then we move the result from a vector into a scalar register. And then we check if we're done. If we have 5 left, then we're not done. And then we do a 1-by-1 loop right here.
If we have 5 left.
If we have 5 left, then we fall down here and we add 1 and we increment, compare.
Sorry, where did the number 5 come from?
You said 5.
Oh, okay, all right.
Yeah. So yeah, if we have 5 left, then we come into this 1-by-1 loop, and we would run this 5 times, and then we would fall through and pop the stack. This is a historical thing, and then we return. So yeah, a bit complicated, you might say, and you can imagine like this function is as simple as it gets. You could imagine, the difference between release small and release fast for a whole project is kind of a lot when you look at this.
Yeah, it's
right?
like, what, 10 times more code?
Yeah, so this can be really fast if, you're spending a bunch of time in here. But if you're not, which is another possibility, what if most of my arrays only have 5 elements and I'm passing it into this accumulate function? Most of this is dead code. Most of it is not useful. So,
It might even be slower.
yeah.
Well, I
Yeah.
guess it wouldn't matter if it's on 5.
Kind of would.
Well, it might matter if you're doing a lot of arrays of 5.
Well, then I should rewrite it, so.
Yeah, so I just want to show you, we can actually write code that does this fairly easily. You know what, I'm not gonna do that per se, but I will say, first thing that we can do to try to make this better. Firstly, we test if it's 0, then we test if it's greater than 32. So one thing that you can do is you can, sorry, I'm just considering how to do this. One thing we can do is we could say if nums.len is 0, unreachable. So maybe it's the case that in our real code, we're like, okay, we're not going to have a buffer that is a size 0. So that eliminates one of the jumps, right? Another thing we could do, see if I remember my hotkeys here. So let's do.
Can the CABI handle errors?
So unreachable, this actually is not going to return an error. I'm actually saying it's impossible. So what I'm doing here is I'm saying if nums.len is not a multiple of 32, that's impossible. So it's always a multiple of 32.
So your
And
function is
that-
limited to handle.
That doesn't have to do with the CABI. That's a Zig idiom that's going to give instructions to the compiler of what it's going to generate.
Yeah, unreachable means like,
The compiler will error out if you try to do something that would cause it to get to an unreachable.
yeah.
God, because in my code, I usually do the same thing, except instead of unreachable, I say return error dot nothing or something. And I realize I can just optimize all that away and make unreachable now instead of.
Well, yeah, you can see there's significantly less code here. And this actually shows a practical strategy that you can use. I was actually in a Discord the other day where someone was talking about how they're making their programming language written in Zig. And they were discussing this SIMD optimized function that they made for something relatively trivial like this. And talking about how, like, oh, if we do this work to optimize this function, you know, my programming language is going to benefit from this. And to me, I'm like, well, first thing you should do, just overallocate your buffer. You know, like, just make it so that we can jump mostly straight into the steady state of the loop. And, you know, for something like this, where we're adding a bunch of numbers together, you can put zeros at the end, right? So me showing this unreachable code here, this is just for demonstration purposes. In real code, though, you can do this, where you can put zeros at the end of a buffer, just overallocate a couple of bytes, and this can dramatically reduce the amount of code that's actually needed to perform different tasks. Now, with a lot of the SIMD work that I've done and presented on here at Vivint, there's actually a lot of good reasons to want to do this, which is that, you know, anytime you're expecting the compiler, let's say, to turn this into a SIMD equivalent of your code, it's going to have an epilogue, like we saw, where it's going to say, okay, if it's now we need to go check one by one. One of the things that I showed is that we can do tokenization entirely in SIMD. With my most recent talk that actually Jeff missed, but yeah, we can do it entirely in SIMD, and so it's almost a requirement, I would say, to just overallocate the buffer by a little bit. That way we can take 64 bytes at once, 64 bytes at once, 64 bytes at once. That way we don't have to have a cleanup loop at the end, which would basically be a conventional tokenizer, you know, with branches every other line in the assembly, just to get the last 5 bytes, you know. So we don't want to do that. We don't want to have to deal with that. So if you can, pad it with zeros, pad it with tens, whatever makes the most sense for your problem. this is something that we can do. So this is the first thing I wanted to show. Are there any questions about that?
Well, what's the cost of padding in with zeros?
Virtually nothing. The problem is that when you don't pad it with zeros, so typically, right?
I mean, like, could you pad it with zeros somewhere and
In the function?
see what that looks like? Or, I mean, can we SIMD pad it with zeros?
So what you could do is there's a couple ways of doing that. You could like write each one to the stack and have the stack be zeroed before you do that. And then you could pull it back out. So you could round trip to memory or your cache. You could do that. That wouldn't be the best way to do that, either from a speed perspective or instruction count perspective. What I'm trying to say is that when you allocate it in the first place, just round up. That's what I want people to get from this part. Just round up. We have functions for that. I believe, does anyone know what it is? scd.math. I don't know. There's a function for this that's in the standard library, and it will just round it up to whatever you want. And yeah, even if it's not in there, it's pretty simple math. You just.
But then you do potentially have the complexity of needing to track length separately to know. Do you need
That is possible, yes.
Okay.
When it comes to this problem, you wouldn't have to, but yes, if for different problems, you might want to do that.
Well, if I needed to do the average,
Mhm.
I need to
Yeah.
accumulate it, let it put in the extra zeros, and then divide by the actual number.
Yeah, there are some things you can do, like what you could do is you could say, okay, this nums here, it's going to actually pass around with it the actual length, but as part of the contract of my code, I know that the allocation underneath it is rounded up. So you can do that, and I have done that. But for safety purposes, I recommend like put that in a struct, where call it something like rounded up memory or something, and then and so it's part of the contract of your code where you're like, okay, I have this slice, and I'm going to pass in the actual length with the slice, but when I deallocate it, I just have to know I'm going to bump that back up to what it was that I got back from the allocation. And yeah, just make sure that your allocator doesn't give you too much in that case, I guess. But yeah, so this is something we can do for a lot of speed. But there's a problem with this as well. There's a bug that can happen. Does anyone know what it is? Oh wait, you had a question as well. Do you want to
Yeah,
go?
I was gonna say, why does it do 4 vectors? Is there like a ZMM4, or is that just?
There is, yeah. So for most of the register files on x86, you're going to have 16 of them. So if you have 16 general purpose registers, and you have 16 XMM and YMM, but with AVX512, there's actually 32. They just decided to add more when they added the AVX512 instructions. So there's actually 32 ZMM. It goes up to 31. Yeah.
But that could be like another optimization you could do if you were doing like even bigger.
Probably not, because we can do 4 of these adds per cycle. We can start 4 per cycle, and then we can probably do this add, and yeah, we can probably do this add. The compare and jump not equal. These will get fused, and yeah, so we might actually be able to do 1 iteration of this loop per cycle.
Would it not help for pipelining to?
Oh yeah,
like the same instruction. Or
it might actually just pipeline this. Like if you looked at I'm gonna pull up a pipeline analyzer a little bit later, so we can see if pipelining is happening. Remind me if I forget. But I want to go to the next thing. So there's a bug in this code, and in Zig we try to not have that. We want perfect software. And so what you can do instead is you can do this plus bar equal. So the thing about plus
Wait, what
equal,
was the bug?
Oh, is it, overflow?
overflow. So the
Yeah,
thing
yeah,
about-
I was wondering about that when you first defined it, but then yeah.
Yeah, so this plus operator, right, implicitly is saying it's undefined for it to overflow. And we have a couple of different ones. We can do modulo, where we say it's defined. It might overflow, and that's what I want. I want 2's complement integer overflow. Or you can say plus bar, and plus bar is saturating arithmetic. So saturating is where, if we add these numbers and they go over the boundary, it will actually just stay at the boundary. That's what it will give back at the result. So for like an 8-bit value where the maximum is 255, if I say what's 200 plus 100, saturating byte arithmetic, I will get back 255. It will just clamp at the maximum value.
Okay.
Same thing happens for the U64. So,
Is that naturally converted for subtraction than the 0? Or,
yeah, so for subtraction, with subtraction, when you're subtracting a signed integer, right, you could go either way. And yeah, it will clamp whichever way you're going. Like, it does what you expect. It does what you expect. But that does mean it's a little trickier if there isn't a built-in instruction to do a signed version from the instruction perspective. Okay, I actually wanted to show, there's one way of dealing with this without invoking that I actually wanted to show first. So one thing we could do is we could actually try making this potentially errorable. So we could say error.overflow, let's say. Sorry. Still new to this keyboard. And let's actually just take the standard library in, just because there's a couple of helpful things. Okay. So what I want to do is I want to try to keep this branch free in my hot loop. So I'm going to make this potentially an error, but then if it is an error, I'm going to return that, for the purpose of it being a U64, I'm going to materialize that as the maximum U64, let's say. So yeah, you can see I already gave the game away, but let's just do it. Dot math dot max int U64. Sorry. This is going to be what we return. So if sum, and yeah, typically, you might want to like prefix it as like air sum when you define sum instead. But yeah, in this case, I'm just going to do it like this and say we can return the non-error sum like this. And then if there is an error, then we return the max end of a U64.
Now, how is that different?
Okay, and then we need to do sum equals add U64, and we're going to add sum to n. And did I mess this up? Oh, you need to write it like that. Maybe they got rid of that. So, right. You can do. You could do that. What I actually want to do is I want to say. I kind of wanted to see if anyone would get what's going on here, but it looks like Zig is actually forcing me to show it, which is good. But yeah, we could say if some yes.
This doesn't feel branchless.
Yeah, I was trying to trick you a little bit, but it's not going to be branchless. That was the point of this. Okay. So yeah, it's not branchless. This kind of code, it actually can be materialized branchlessly on one particular architecture of the mill, because you actually can have this this error follow around a value on that machine. But yeah, on most machines you don't have that. So I was just going to show that, and yeah. So let's actually just go back to what we can do instead.
I had another question, which is, here we're using 32 because you're on a Zen V5, correct?
Yep.
So if I'm on a different architecture, I guess 32 is still safe on another architecture because any, you know, it would be 8, it would be 16, it would be whatever.
Mm-hmm.
But is there a
Oh yeah.
good way
Okay.
for me to make it
I understand your question.
compile to the architecture?
Yeah. So I was talking about, you probably want to over allocate maybe to the tune of 32. Typically I'll just over allocate to 64 bytes. This is actually saying 32 8-byte values. So that's what, 256? So yeah, so what if I'm on a different machine and it's not 32, but I want to over allocate my allocation on that machine? Should I over allocate it by 32 elements or a different number? So we actually do have something for that, and I'm just going to pull up the documentation because I don't have IntelliSense on Godbolt. So let's go to docs and standard library. Blow it up a little bit.
By the way, to those of you watching on YouTube, feel free to ask questions in the comments, and I'll try to field those as I can.
There you go. Suggest vector length for CPU is what you want to use. We click on that. So what this will actually take is a type. If it's U8, that's the basic one. And then you pass in the CPU target. And do we have the implementation here? Yeah, we do. So this actually just says, oops, sorry about my mouse. This actually just says, if it's x86, you know, check, is it AVX2, is it AVX512, right? And it will actually tell you, like, how big is the vector in bits, is what this one is telling you. But then, based on the type, it will divide by the bit size of the type, right here. So, so this suggests vector length for CPU is the answer to your question.
Okay.
So yeah, if you're on ARM, for example, that's going to go in here. This is your ARM 64 versus ARM. We got AArch 64. It's a really dumb convention, but it is what it is.
Why is it dumb?
Just the fact that we have ARM, that's the 32-bit one, and then we have AArch 64 for the 64-bit one. That just seems to me to not be a good naming scheme. And yeah.
Well, it's consistent with the other inconsistencies.
Right. There you go. I actually saw just the other day someone was confused about this and what this means. So what this is specifically checking, it's checking, do we have SVE? And this comment is about this. SVE is a scalable vector extension. And this actually means that the hardware, or sorry, the instruction set doesn't define how big the vectors are. That's actually defined by the hardware. And in Zig right now, I don't know that there's really a good way to program for that. So I don't really think about that. But your MacBook doesn't even have that anyways. You have Neon. So you're going to have 16-byte vectors.
Dare you insult my MacBook?
You don't want SVE. It's not that good anyways.
Okay.
My opinion.
I trust your opinion.
So So yeah, neon is a pretty good instruction set. And I can share that a little bit if we want as well. We can actually just like clone the compiler, and we can say, which CPU do you have?
This one's the M2.
M2? Oh, almost upgraded you on accident.
No, you can upgrade me. I'm happy with the upgrade.
I'm pretty sure the EMIT is like the same. I did look at the optimization guide for the M series. And yeah, you have to like have an account in order to look at it. So it's kind of funny. Okay, so yeah, let's look at this real quick. You can see this STP, I believe this is a store instruction. Yeah. So this is taking the stack pointer and we are subtracting 16 from it. And we are writing X30, I don't know, STP. That's store, right?
I've
think-
never
I think it
worked
is.
with this one. I've only ever done x86 programming.
Yeah, we do a similar thing. We add, this is actually 32 at a time as well. And
Yeah.
you see we have roughly the same thing going on.
Except it's easier to read.
A little bit, yeah. This instruction set architecture actually has this add P, and I suppose that's a horizontal add. So this is actually doing the same thing as this.
But wait, I thought we got rid of the horizontal add with the unreachable on the left.
The horizontal add is where you end up with 4 vectors full of accumulators.
Oh, okay.
You add the vectors together, and then you accumulate the one vector into one value.
Okay, right, I remember now.
Yeah. So there you go. And then, yeah, there's some fun things about ARM. Okay, so I wanted to show, this has a bug, it can overflow. And so what we want to do in Zig is we want to specify what happens. I attempted to write out what it would look like if you were going to try to error without using try or catch. With try, it's actually a lot easier. Just with the C ABI, you don't really want to deal with that kind of thing. What we can do is we can do saturating arithmetic. And so if it crosses over the boundary, then it will actually just stay. Now you can see our SIMD went away. And
Oh, no.
if we look at Apple, it also went away. No SIMD. Very sad.
Well, how do we reconcile this?
Well, we can reconcile this. But yeah, the compiler actually could do this, it just doesn't. But yeah, if you want, you could say, okay, give me a vector of, ooh, am I getting, that was kind of cool. It looked like it was animated cursor for a second.
Yeah, that's the...
That's the AI.
I'm not, yeah, it's the AI. It is the AI.
Okay, let's do the suggest vector length thing.
I'm not sure if it's the HDMI box or if it's the TV or if it's both.
So yeah, let's actually take this and we're going to need our CPU in here, so got a little glare from where I'm sitting. So I think it's built-in.cpu, something like that. We're going to find out. Oh. Well, it's because I did the line deletion thing. Not on point with my shortcuts here. Okay, let's compile log this and make sure that gives me the right thing. And it says I messed up. Oh yeah, I messed up this because I didn't finish that. So it needs to be std.simd. Okay, so this one is actually telling me, okay, for my Zenver 5, it's suggesting 8 of the U64s in a single vector. That doesn't mean how much we would do in total. That just means how much it can hold in a single vector. And then we can look here, and it says 2. So that makes sense, because on ARM we have 16-byte vectors. Each element is 8 bytes. You can do the math. And yeah, so let's take that. And
So it's both, we're looking at the total number of bytes as well as the number of vectors.
yeah, it's telling us how many 8-byte values can we fit in a vector. So that's what I'm going to write right here. Now, okay, sorry, this is a new computer for me. Still getting used to it. Okay. This is optional, so some machines won't have anything. You could just say like or else 1, let's say. And probably you'd want to move that to a new line if you were actually writing good code. And then we can do splat 0. So this is going to make a vector that is of whatever size, however many U64s we can fit. And we can actually make 4 of these, let's say, like we were doing before. So let's do that. And then we can write 4 of them out like that. We can do this. We also could do, I'll show you in a second. We could write it like this. We could also do std.mem.zeros on the type. So if we take this type and paste that in to here, then that will actually give us back the right value as well. So, okay. So we got 4 of our vectors loaded up, and then we want to load in 4 vectors from nums, assuming of course that we overallocated enough. So how do we do that? There's a few ways. One thing, yeah, what's your question? I'm still working on this line. So what we could do is we could do some compiler magic here, where we're like, oh, I don't want to fight with the type system in front of you guys. It's not good for kids to see that.
I'll avert my eyes.
We don't have the college kids from last time.
Yeah, I was going to say, what I could do is I could make this a slice of those vectors, and then the length will have to be divided by that, and then I could pull out 4 of the vectors each time. So I could do that. I might struggle to type that out in front of you. But yeah, it's easier to just do a while loop with an L if you feel inclined. Okay.
This is a side question I have for you. Is it better to do while true rather than your condition of breaking? Because I always do condition of breaking, but I noticed in your past you always do while true.
Yeah, so it can make a difference, like if the condition is at the top versus the bottom. A lot of times, like if you have a condition that you're checking only at the bottom of the loop, where you say, if we reach 0, then break, that can be better because in the code, how it will look is, like in the assembly, it will go into the loop every time, and then you might branch back, rather than having to check at the top and possibly skip over it. And so, if you saw my last talk, yeah, I avoid that thing for that purpose. But it's not strictly speaking like a recommendation that you always have to follow. But it's just like if you actually want to avoid, for me, like in those loops I was showing in my previous talk, I'm like, okay, this loop is probably going to run once, never more. What I didn't want to introduce was a situation where it might be 0 and it might be 1, and it's hard to predict which. And so I'm like, let's just do the work of doing the loop once, because it's only like 5 instructions. And so I'm like, let's just do the loop one time, rather than pay the penalty of potentially a branch mispredict, which could be 15 cycles. So I'd rather just pay the cost of 5 consistently than run into that. Also, there's a cost associated with jumping. It's not that large, but you can miss 1 or 2 cycles off of that. And so when it comes to trivial amounts of work, you may as well just do it, especially if the CPU is working ahead and it already is done with that work anyways. You may as well just use that. So, yeah. Okay, so yeah, let's pull out for these vectors here from nums. So what I typically like to do, I like to make a cursor that I call cur.
Real quick,
Yeah.
time note, we are 20 minutes away from 9 o'clock.
Okay. Okay. Yeah. So let's make a cursor into nums, and I always do this just to show what it is. This actually doesn't change the type doing this 0 slice. But then yeah, every time I'm going to say okay cur, and we advance it by however many we wanted. And so let's actually make a variable of this saying how many we get at once. And let's call it VLEN for fun. Maybe that's bad terminology here. So we're going to be incrementing cur by however many we pull out. And yeah, let's pull out 0 through VLAN. And then put that into a vector. So let's do a vector of VLAN U64. And can we do 4 at once? I'm not. Yeah. Do I need this here? Okay, so I'm saying for each element in sum, we're going to take that one and we're going to update it like so. We're saying that value added to chunk. And then we need to break out of this loop at some point. So if cur dot len is 0, then break. Oh. Did we get it? Messed something up. Oh yeah, it gives us a pointer. We got a dereference. Copy the data into the vector. So, what's the problem now? Yeah, we have to reduce sum. So we say sum 0 plus sum 1 plus sum 2 plus sum 3. This is adding the vectors. I also could have done it like this, where I say var final u64 equals 0. Sorry, watch me type here. Final plus equals s. Do the same thing. And then we want to do an at reduce. Why is it not like this?
No brackets.
Oh yeah, because this has to be the type of sum still. Or the type of this. There you go. So we add the vectors together, and then we reduce the vector of final by doing add. We need a splat. There you go. And I got the parameters in the wrong order. There you go. Okay, so we did it. So this is going to do the same thing that the compiler did, all this code. So you can kind of see like this is part of the issue here. So if we want to change this to be saturating and saturating, and this one, do we have a saturating add? Can we do that? Like sat add or something? I don't remember if we have that. I wish we would print it out, honestly. Let me see if we have it real quick in the reduce ops, because we might not. We do not. So that means you gotta type it yourself, I guess.
Yeah, that's right. Oh.
Okay. Now we do an inline for 0 through VLAN, because we can't actually pass a vector into that for construct, and then we take that plus, and we wanted to do saturating the vector. Oh. There you go. Okay. Now, this does what we want. So this is now correct code and it's vectorized. So there you go. That was way too hard. Hopefully we can make the compiler do this automatically. But yeah, what this will do, like I said, it'll add the U64s together. If it goes too far over, it will just stay clamped at the maximum number, and you can use that as like an error value or what have you. And yeah, you can see on x86 we actually do not have a specific instruction which does this. It's a combination of a min, a VP turn log, I believe, and then an add. So we actually have to do 3 instructions for that. ARM actually has 1 instruction for this. We can do UQ add, which is actually our saturating addition here. So anyways, now that I spent all the time on that, I wanted to kind of show just a quick rundown of exactly like what operations we really have on SIMD. So one that I really like is A64 ARM, what's it called? Give me a second. Gotta remember the person's name that made it, because that's their website. Here it is. It is douglej.github.io/ASIL. And yeah, this is a list of the ARM instructions. We also have the x86 ones right here. And you can look at all the ones that are available through here. So there's a few main categories. A lot of them you can actually test for in Godbolt. So it's relatively easy. You see we have this vector syntax. You can, let me just open up a new one so we can do that. If you want to test to see like, oh, does the compiler support this? You can just say, okay, let's make A be a vector of let's say a vector of 64 U8s. And then let's make B do the same thing. Oh, wrong button. And then I want to get that out. And then let's say I add them together. And let's do this one. So yeah, using Godbolt, you can a lot of times you can ask the compiler basically like, do we have an instruction that does this? And right now we have an extra one of those. There you go. So can we add 64 bytes to 64 bytes? You can see it actually is going to turn into 4 instructions on this ARM machine because we only have 16-byte vectors. So it's going to pass it in as 4. Right here, you see we do have one instruction that does this. And you can do things like, okay, let's do saturating. And in this case, you see on ARM, we do have an instruction for that. And we also have one on x86. So you can kind of see like, oh yeah, we have it for byte granularity. But if you turned it to, you know, a 32U16, for example. Oh, wrong button. There we go. A 32U16, then you still have it. But if you turn it to a 16U32, then you don't have it. So there you go. You can figure out which operations exist, and you can do things like, okay, tell me, you know, for each of these 16 4-byte values, which ones are, which one is it the case where A is greater than B, and this value will be returned. It'll be represented differently based off of the ISA, but in general, if we look at the error here, it will tell you this returns a Boolean. It should be a vector of Booleans. Oh yeah, it's because it's looking at this. Okay, so yeah, it sees 16 Booleans. And so if you look at this, what you can see on this AVX 512 machine, we do this comparison and it's writing out to a K register. This is basically like a bit mask register. It's just going to give me 16 bits in this case. On ARM, we don't get that. Instead, what we get is we get a vector where each resulting element is going to be all ones if it's true or all zeros otherwise. And if we actually want this to be materialized as the bit string itself, so we could do something with that, we can do a bit cast. And we can turn this into a U16. And this will actually give us, you know, our 16 answers where each bit is one of the answers. And then we got to change the return type. There you go. And you can see on x86, right, we just move this over. There's a K-move instruction. On ARM, we do not have this. And so there's actually, you need to do a routine in order to actually accomplish this operation. So different things will work differently. If we actually turn this to, let's say Zenver 3, this only supported AVX 2. You'll see we also do not have that instruction that does the whole thing either. And so this, we actually will use this move mask instruction to extract the answer. It doesn't actually matter, but just the point is, you know, based off of the instruction set, it's going to be able to do more. It's going to be able to do certain things and not be able to do other things. So this resource here will be able to tell you what are the things that are supported on x86. This is officedatime.com/SIMD512E. And douglalj.github.io/acyl. This is the A64. This one's technically for the SVE instructions, but yeah. So for SIMD, you have a couple different classes of operations. Let's just open up zip here so you can see. We have operations that take pieces of data and mix them around. There are general purpose ones. On ARM, it's called table, TBL. And I don't know what it's going to show here. Okay, yeah. So for this one, this is something that I showed in my previous talks where I'm like, okay, I have a vector of indices, and I can move things around in the vector using the vector of indices. That's one way of doing it. On x86, we have, can I open this up? On x86, we have VP chef B. Not that one. Oh, it's just a chef B. Okay. So you have VP chef B and vperm B. So these are your two classes of shuffle. One of them only has 16 bytes at a time. So that means when we do a 32-byte VP chef B, it's actually just looking at each 16-byte chunk. And when we do 64-byte, it is also just looking at each 16-byte chunk independently. That is for speed purposes. And then a permutation is where you can go cross-lane. And so you can actually do 64-byte anywhere to anywhere with this. We actually have vperm2, which can do 128-byte. 128-byte lookup table. You can look up 64 bytes into it at once. And yeah, on ARM, we have a TBL, I don't know if it's going to show it. We have the ability to pass in up to 4. This is a TBX. We have the ability to pass in up to 4 of these shuffle vectors at once. And one of the things about ARM is that it actually has these interleaving instructions, which can make something faster. And I have a blog on a couple of examples where, let's see here, use interleaved vectors for parsing on ARM. So the idea is, instead of reading in data like this, I showed in one of my earlier talks, you can read in data in an interleaved fashion. And that means that a number of operations that you would do on ARM, you can actually do faster. So when we load in 64 bytes, this is what it looks like normally. And when we load it in interleaved order, it's one instruction. This actually is more expensive slightly than this, but everything else is cheaper. So I show, originally the motivation for this is if you have a struct that has RGBA, it will decompose it for you. So you have a vector of R's, G's, B's, and A's. This is what is referred to as a gather operation. But yeah, if you want to do a move mask, which is kind of what I was showing before, where I say, I want to figure out some piece of information about all the things and get a bit that tells me the answer. By default, you get this long thing from LLVM. And this is on x86. We kind of saw a version of this. On ARM, you can do it like this. I actually showed step by step how this works in one of my earlier talks. But you can see it's a lot shorter. And this is something that's going to be more efficient, especially if you're going to be doing a lot of these. So I'm just trying to go quickly through this now. There's an unmove mask that I show requires a lot less. So you can actually eliminate all this stuff here, where you're loading in all this data. You're doing TBL to do vector shuffles, and then isolating individual piece of data. Here, we can do better. So point of the story is, if you're operating on byte data for ARM, use interleaved. I also show with element-wise shift. I talked about this before, but again, but one thing that's interesting about interleaved space is when you're like, okay, give me a vector that's the byte prior to this one, which is something that we have to do a lot in parsing. And then I say, okay, give me a vector that's the byte prior to that one, and the byte prior to that one. So that's what each of the numbers represent. If I have bytes that are 0 through 15, the one that comes before it is -1 through 14. And I actually, this is an improvement that I came up with for UTF-8 validation. We can take this interleaved vector, and if we look at it, we say, okay, this second vector here, the byte that comes before each byte in the second one is the first one. And the byte that comes before, each one in the 2, 6, 10, 14, 18 right? That's 159, 13, 17. So, so yeah, I have an article on it if you want to go slower through it, but that's what we can get on ARM. Anyways, so let's be done with that. Oh, that's a different thing. Okay, I want to go back to my one slide here. Okay, so in my previous talks I showed, when we're parsing, what we can do is we can produce a bit string that tells us some piece of information, like where are the alphanumeric or underscore characters. And then using simple bit manipulation, we can figure out where does that start and where does that end. Up here, I denoted start as the, the open brace, the less than symbol, and then the greater than symbol is going to be the close. And so, you can get groups like this. You can do, and you can use an operation called a vector compression, and this is the fundamental operation that enables the stuff that I presented last time, which is that we can take some bit string and we can compress the indices in a vector. So we can get the start indices and the end indices. We can subtract them from each other and add one to give us the length. And yeah, that's all I wanted to show for that. I wanted to show something else we can do. This is a VP mad WD instruction. This was actually added to x86 for AI. So apparently this is a useful operation in some AI workloads. Here's another reason that SIMD gets added. So this being a very common operation, we have a lot of what's called dark silicon on our CPUs that's not doing anything, and that's by design, because if everything on the CPU was firing all at once, we could overheat, we could melt the CPU itself, and so what we end up with is a lot of the chip that is unused, but actually that we want to be unused, and we can stick more things in there. And so one of the things that they stuck in there is this VP mad WD instruction. And under the hood it looks something like this. We have 16-bit elements of A and B. We multiply all those together, and we actually get those out as a U32. And we add each pair of them that are adjacent together to get a 32-bit result in our destination. So this is something like what it would look like inside the CPU. We have some multipliers that we feed each of these elements from the vectors in. And we would actually have a lot of these. So we would have 32 of these next to each other inside the CPU. So this is one of the reasons why we have a separate vector register file than scalar, is because it takes up a lot of power to actually run it. Imagine having 32 of these units copy and pasted. It's simply a lot of wires. It's a lot more than 64 multiplying by 64. Here we have 512 bits interacting. So I just want to show with this one that we can actually just write out what we think it does, and the compiler can give us this instruction. So let's go over here and try that real quick. Okay, so what did I say? I said we have 16 bits. It's a 512-bit vector, so let's try that. So we have U16s, and that's going to be 32. And what is the result? It is 32-bit values. There's going to be 16 of them. (16 U32s) is the result. Okay, and then what we do is we take each value of A and B and we multiply it, but we want to make space. There's got to be 32 bits of information there. So we're going to cast A to be a vector of 32 U32s. And then we multiply that by B. And it will implicitly cast up B to be the same. So we do that multiplication. And yeah, let's call it result. And then we add each pair of elements. So the way that I would typically write that is we can say std.simd.deinterlace to R. That's not an R. So what this is actually doing, this deinterlace function, it's going to take R and it's going to say, okay, first value goes here, second value goes there, next value goes here, next value goes there, and so it's divvying up. So every other one is going in to a different vector. So we actually get out two values here. So this is actually going to be a 2 vector of 16 U32s. So hopefully that makes sense. So we split up R into 2, and we took every other one. That's what deinterlace means.
So now we got left and right channel of audio.
Yep. And then we do return x 0 added with x1. So this is the part where we are adding the pairs, and then that has the correct results.
In my understanding is in neural network work, which you mentioned, is used to speed up the dot product, which is how you make a prediction with a linear regression, which a neural net is basically a bunch of linear regressions tied together. So this would make that much faster than calculating it normally.
There you go. So if we upgrade to a machine that has that instruction, hopefully we don't get it. All right, that's not what I wanted. Maybe I messed something up. 32, yeah, 32, 60. Well, let me go to GitHub. Yeah, let's look up LVM GitHub. And I'm missing an H, but that's okay. Luckily, I did this before. That's why you don't try to do stuff live.
I think this is better because that happens to me all the time.
Yeah.
So seeing you work through this, I'm like, okay, I can do this.
So they actually just fixed this one here, and I wrote this canonicalized instruction here. So what did I mess up? It's signed. That's what it is. It's signed, everybody. That's the problem. So this has to be an I32, nope. Lowercase. Okay. No, still messed up. What's the problem?
It doesn't like the
Is that
plus on
what
line
we're
7.
The return type.
16. Oh yeah, that didn't get changed. There you go. There you go.
So is line 7 concatenating the two vectors? What is that doing?
This is an addition. It's a literal addition,
But,
like this addition. It's not concatenating.
hold on, all right, I got confused about something then, because the
Sure.
deinterlace, I thought this was producing two vectors.
Yep. And then we take the first vector and the second vector and we add them. So what this is ultimately doing is it's adding the adjacent values together. Like it has now condensed the adjacent values into one value through adding.
But the interlay separates it into the even indices and odd indices. And
Right.
Okay,
Right,
so
yeah.
if we were to print or debug print x sub 0,
Mm-hmm.
that itself is a vector.
Yeah, that's a vector.
Okay, so that's why I'm
It's
confused.
it's a vector 16 of I32. This right here.
So line 7 is re-interleaving the values to add them, or it's concatenating them together to add them?
It's just adding two separate vectors.
I don't understand what that means.
It means element-wise, it adds them together.
So adds 0 and 0, 1 and 1, 2 and 2.
Yeah.
So it's,
Yep.
okay.
So over here, we added the pairs of values, and the way that I did that is I de-interlaced it, where I got the even ones and the odd ones, and now I'm adding those. And at the end, you can see we get A0 times B0 plus A1, B1. Okay. So that's what we're doing. And,
I'm just
and
not familiar with that syntax. The only place I've ever seen that was, something like that was in Rust,
okay.
where
My
you could
question is
add
that
non-scalar value, printed value.
is the type of const R.
Mm-hmm.
Uh,
That's going to be this right here.
Okay, so we brought in, sorry, I read 16 comma, I read 16 comma, I32 for the input, not 32 comma I16 for the input of A at the top, so I was confused by R.
Yeah. So yeah, we read in 32 2-byte values,
Yeah,
and then we multiply them, and we get 4-byte results.
yes, that was.
And then we reduce each pair of 4-byte results by adding them. Each adjacent pair of 4-byte results, we add them. And that is, in fact, one instruction over here. So sometimes you can just say, oh, there you go. Or you can name it something reasonable if you don't like the cat across the keyboard naming convention. And and yeah, there's actually another one where you can take in one of these vectors, an accumulator variable, and you can add it to the result. And they just fixed this. Let's see if it works. Probably will not. But if you add z, that is also going to be one instruction next time LVM updates. It is actually this instruction here. This is me complaining about it. It is VPDPWSSD. I definitely feel like that's a cat naming convention. Like just, oh yeah, there you
Enter
go.
password.
Oh, that's a great name for an instruction right there. So just put VP in front of it so you know it's a vector.
That's how I felt the whole time,
Yeah,
from EAX on.
yeah. So, anyways. I want to show one more thing. Branchfree.org. This is a website I really like. There are a couple of blogs I really appreciate. This one's by Geoff Langdale. We have one from Daniel Lemire. He's written a bunch of really awesome things, like SIMD JSON being the one that influenced me the most. But yeah, if you click on his profile, he has like a million things that he's contributed to computer science. But this is his blog, and it has a lot of SIMD stuff. There's also ox80.pl, Poland. And this is actually this person. I'm not sure how you pronounce that properly, but
That's Wojciech Muła.
there you go. I would not have guessed that. So there you go. But yeah, tons of stuff for SIMD and SWAR in here. If anyone wants to look deeper into that, goes back a long time as well. And yeah. So let's go back.
Do you know if for like data transfer from CPU to GPU, it's faster to use the SIMD registers rather than
So I guess I'm not sure on that specific question, but the thing is, like, when you go into a GPU, like, the thing about SIMD is you can do it on the CPU. It's more local, and so it's going to be faster to do it on the CPU if you want to do it on one thread. If you don't want to do like as much as you might want to do on a GPU, that's the main thing that I would be thinking about for that. I wanted to show this article, not that one. Yeah, there you go. That's Altman.
Oh, you're right. Sorry.
Different.
Altman, different sim.
Yeah.
Before we end tonight, I do have my doom and gloom,
Oh, no.
world-ending apocalypse controversial statement.
Oh yeah, we always got to fit that in.
Yeah, and it's about Sam Altman. So.
Okay. So there are three kinds of SIMD usage, quote unquote. And the first one is horizontal. Do lots of simple things at once. I feel like typically horizontal might be used to mean something else, but yeah, he says, we want to do something simple. We repeat it over and over again. That's basic SIMD. We can also do vertical, do a really big thing using our SIMD resources. So one thing that we can do is we can just hold a lot more data, or we can do what Geoff Langdale says here. He has a non-deterministic finite automaton implementation with 512 states at once. So that's pretty cool. And then there's exotic, where this is SIMD-sized things. So one example is this instruction. This is a carryless multiply. And carryless multiply is basically like a multiply, except instead of add, we do XOR of all the values that are intermediate. So we just are not carrying. So this is used for cryptography a lot. It's also used in parsing to do the parallel prefix XOR. It doesn't really matter what that means, but let me open up this.
And there's a gallows field instruction.
Yeah.
Is that even real?
Yeah, the Galois field instruction, it's for basically, you can do arbitrary reordering of the bits, and this is actually used for things like a bit reverse. So if we do a bit reverse.
I think I saw that in some BLS cryptography, but it may have been something else. There was a GF something earlier.
So yeah, if we return bit reverse of x, and then we make x be a U64. Okay. We use the Galois field instruction for that. It's also used for on x86 we don't have like byte-wise shifts in the vector, and so that can be emulated with 2 byte-wise shifts and an AND. But on AVX 512 we can actually use this right here to arbitrarily reorder the bits, and you can kind of see that too. Like these are all powers of 2, and it's kind of backwards from what it will be actually. So this is actually, when we pass this into our Galois field affine multiplication instruction, this will actually give us the bits in the reverse order of the power of 2 that you see there. And so this will actually reverse the individual bits of each byte, and then we do B-swap to reverse the bytes of our 8-byte value. So yeah, Galois field. You can do some crazy stuff with that. I wanted to show this real quick. We got careless multiply. I actually opened a proposal for Zig so that we can actually just do a star caret for that symbol for careless multiply, so you don't have to have a function that does this. But I have a function that does this. And point here is this is the CLMUL instruction he was talking about, careless multiply. This is operating inside of a SIMD register, even though, like, in this case, we're actually only dealing with one thing. Like, we want to multiply A times B, and we have two of these for some reason, because, oh yeah, this was an interlace. We don't need that. Let's just do the careless multiply. Well,
Down towards the bottom. Is that the
oh, I guess these are all same arguments. Okay, but yeah, we can do. This is the careless square. This is used for interesting fact about careless multiply. When you careless multiply a number by itself, it'll actually move each bit at position I to position 2I, and so it'll pad it with zeros. This is a property that is useful sometimes, I guess. But yeah, let's go to the end and give this a y, a y, and a y. So So you can see on x86, we have to use the, oh, it's still getting upset about this, even though I'm not using it. Okay. You can see we have to use SIMD for this. So, for normal multiply, we don't use SIMD. For careless multiply, we do. Same deal on ARM. Yeah. This is a vector. On RISC-V, however, it's a different story. So let's show that just real quick. So on RISC-V, let's do the sci-fi. And we make this RISC-V. What you see is a whole lot of messing. It doesn't want to do that because maybe it doesn't have it. Okay, let's do the space MIT. I know that has it. I don't remember how to spell it perfectly. This one. Don't let me down, space MIT or space mint. Okay, there we go. So you can see on this one, we just stay in scalar. We don't go to vector. So the fact that careless multiply is done inside of a vector is in some way an arbitrary choice. You could do a normal multiply inside of a vector if you were designing an instruction set architecture and making that choice. For RISC-V, they just decided that they're going to put it inside of a scalar, inside of the scalar operations. And so you don't have to move over to a vector. So the point was, for the SIMD vectors, at the hardware level, it's not just about how we think about it, where we want to do multiple things at once. Sometimes it's just for the fact that it's more data, and so we can do an 8-byte times 8-byte careless multiply. We can do that, and we can get out a 16-byte result, right? We can do that if we want. Whereas, on x86 and as well as ARM, when you want to get the upper 64 bits of a 64-bit times 64-bit number, you have to use a separate instruction for that. And actually, it will always do the lower and higher for just that instruction. So if you're actually using both, it will do the lower end twice. That's an inherent inefficiency, although nothing compared to the rest of the CPU. Most of the CPU is doing work like in the scheduler and like figuring out how execution's actually going to go. So I just wanted to show. Thing is, the SIMD registers, sometimes it's just used because they're bigger. You can just fit more things in there. So that was that.
All right.
There you go.
Well, thank you very much. So, a couple of things. I want to see if anybody has questions. All right, next thing is January. Andrew, did you say you were going to come up with something beginner friendly?
Yeah, I was gonna do an introduction to low-level programming through Zig. That's
Okay, let me check what date we're looking at there.
According to the,
Okay.
if you have something else you'd rather do, by all means. You just had said you wanted somebody to talk about that.
No, I wanted to look at the date because a lot of the meetups are canceling the first meetup in January, but we're not anywhere in the holiday zone, so we should be good. Yeah, all right. Yeah, if you will give me a description for that on Discord, I will update meetup. And then, does anybody have something they want to hear about or present on in February?
I can do something in February, but it's just it's less educational from my side, more like trying to understand best practices and things. And because the project I'm currently working on is making a game engine in Zig to like low-level programming.
Okay.
That could be really cool.
Are you on the Discord presently?
No, I'm on the meetup.
Okay, you're on meetup. Join the Discord real quick.
Okay.
If
I can
you
do
are-
that once I get back to my house.
Okay, yeah, and then hit me up. I'm CoolAge86. What do you know what your username will be? What it is?
Probably BPHILIP, something like that.
Okay, all right, I'll keep looking for you. Yeah, so let me know. I'm just gonna make a note here. Just a quick note. So, Andrew, you said intro to low level. Zig is an intro to low level programming?
Yep. Something nice and beginner friendly.
All right. And
Right.
Um,
And just like, I guess, Zig coding style slash game
those are worlds apart, but we're gonna go with it.
engine. Yeah, I was trying to learn low-level programming by building that.
That's cool.
It's a good way to do it.
Yeah.
I'm coming from a Python background, so I was like, oh, what are
Hey.
what are-
I was a professional Python programmer for years.
Yeah. It's so useful for data science because you don't need to think about any of that. You just go, here's the package.
Are you a data scientist or?
Yeah, I usually use it for data science. I do biomedical engineering at the
Nice.
And then I realized after writing a paper on one Python project that I don't really know how to code, but I should learn that.
So-
Should's a strong word.
Are you PyTorch or are you
Some
TensorFlow?
benefit.
I am whatever you need me to be for the project. Everyone has like an opinion. I first learned on PyTorch, but if your project uses TensorFlow, I'll solve it with TensorFlow.
Cool.
Is there one you prefer or just whatever?
Personally, I prefer PyTorch because you need less coding, just more set up your pipeline and get going and try to like,
Have you ever used Keras?
Are we still live?
For
We're still live.
whatever you name, I've used.
We should say goodbye. Goodbye,
fair
people.
enough.
Oh, goodbye, online people. We're going to continue on to the
Were there any
highly
questions they
offensive
had?
conversation shortly. Let me see if there's any. Nope, I don't see any questions.
All right.